Tapi seorang tu dah pernah masuk lah kelas saya kan. Nafan Nafan dah tak ada Ke dia lagi dalam kelas? Nafan dengan apa? Azimi. Azimi memang tak pernah masuk kelas saya lah kan.
Mungkin.
Siapa kenal Nafan dengan Azimin? Betul kan dia orang dah drop kan?
Nafan tu betul. Betul.
Betul, Nafaan tu
Azimi
betul.
saya tu
Yang
masih.
Azim itu saya tak perasan.
Mungkin Azimi tu tak pernah masuk kelas saya kot. Dia tak pernah masuk mana-mana kelas pun lah. Okay. So, sebelum kita masuk, hari ni kita nak masuk chapter 4 on asymmetric key entanglement. Okay. And then apa ni, semua orang dah ada dalam group lah kan? Betul ke?
Dah ada dah, Doktor.
Okay. Session dalam WhatsApp group. So macam saya cakap sebelum ni, saya tak assign lagi mana group yang akan present topik. Maksudnya tu korang tak boleh pilih lah. So dan satu group akan arrange the the sharing session ataupun forum ataupun yang berkaitan daripada industri yang akan ni lah akan kita buat probably dalam minggu ke week 13. So saya tengok daripada list of group ni, sekejap saya share. Kau nampak
Boleh, Doktor.
So my idea is kalau siapa yang tak cukup tu, contoh macam group 5 Zulfadli, Arif Aiman dengan Nur Rizwan ni, saya nak diorang je yang akan coordinate the sharing session ataupun forum. Boleh ke? Zulfadli, Arif dengan Nur Rizwan.
Boleh Doktor, boleh kot. Saya rasa boleh kot.
Tapi boleh juga, apa maksudnya, discuss dengan yang group member dalam kelas ni juga yang ahli-ahli yang lain lah. Daripada kalau siapa yang memang dalam industri dia boleh bagi cadangan ke. Tapi you will be the you all from group 5 will be the person in charge lah. Untuk reach ataupun coordinate the program. Kalau nak simple pun tak apa, just a sharing session, panggil mana-mana expert yang dalam bidang kriptografi ni to explain apa implementation yang diorang ada dalam organisasi diorang. Boleh
Boleh Doktor. Boleh.
Okay. So kalau it's better you discuss jugalah dengan yang lain. Kalau yang lain pun ada cadangan. Tapi macam saya cakap lah, group 5 will be the person in charge lah, the coordinator. Okay. Yang lain ni saya akan tulis lah which topik yang korang akan buat probably by next week lah. By next week. So next week, okay, kita balik kepada scheme of work tadi. Okay. So week 5 okay. Week 5 online lagi. Week 6 public holiday. Week 7 still online lagi. Sama dengan lah. So ada tiga lagi lah. So starting from week 9 lah. Week 9 ni dan seterusnya akan jadi physical class lah. From time to time saya akan ni lah. Tapi saya akan beritahu next week jugalah which group dapat topik mana, so that korang boleh prepare lah. Macam saya cakap sebelum ni, every person will have will take the opportunity untuk present lah. Saya tak nak dalam satu grup tu seorang dia present. Setiap orang kena on the topic assign lah. Okay. Ada apa soalan setakat ni?
Tak ada, Doktor.
Okay. So assignment pun semua dah hantar lah. Kecuali itulah saya mula ingat Nafan tu kenapa dia tak hantar kan. Lepas tu baru saya perasan dia betul coordinator Postgrad beritahu dia drop. Tetapi semua orang saya dah dapat lah assignment 1. Okay. So saya masuk chapter 4. Okay. Chapter 3 sebelum ni pasal symmetric. Kita dapat nampak the main process of symmetric is apa? Substitution dengan
Transposition.
transposition. So it relies on these two process. And then the substitution tu pun based on the table, a specific table yang dipanggil apa? Apa nama? Kalau ada ES, DES, dia akan ubah substitution process tu based on apa?
Table tu kan, table calculation.
Apa nama table tu? Apa nama table? Siapa ingat lagi? Okay, substitution box, S box. Daripada DES lagi and then sampai ke ES yang masih lagi digunakan sekarang ni. Dan certain algoritma pun mesti akan ada dia punya simetrik lah. Maksud saya simetrik, dia mesti ada substitution box sendiri. Yang fix, maksudnya dia tak berubah-ubah lah value dia. Kalau ES 128 ke 256 ke 512 ke, dia punya substitution box sama, dia tak berubah. Dekat cara implementation dia punya mode implementation of symmetric encryption pun, kalau dia buat CBC, cycle block chaining ke, apa lagi yang mode dalam AES? Saya dah mention kan, mode ni maksudnya tengoklah dia nak implementation kat mana, dia nak buat untuk data encryption ke, dia nak communication encryption ke. So certain mode dia tak sesuai kalau contohnya nak guna untuk data security. So ada mode-mode yang berbeza dalam dalam AES specifically lah. So cara implementation berbeza. Algorithm dia still sama. Cara proses dia lah, maksudnya sama. SBOC pun sama. Tapi cara implementation dia berbeza sikit. Itu kalau untuk simetrik lah. So on chapter 2 kita belajar pasal apa? Chapter 2 kita belajar pasal apa?
Basic number theory.
Basic number theory ataupun macam subjek saya belajar tu dia panggil mathematical foundation. Maksudnya mathematics foundation specifically untuk cryptography. So kalau perasan symmetric encryption dia tak heavily on mathematics. Tapi yang kita belajar chapter 2 tu mathematics foundation ataupun basic number theory is specifically untuk asymmetric encryption. So this one is very heavily relies on mathematics lah. So okay, this is the subtopic kita akan tengok. Okay, so dia relate on dia continuance from the chapter 2. Siapa ingat lagi GCD tu stand for apa dan untuk apa? GCD?
Greatest common divisor.
how it works?
Kita cari pembahagi yang terbesar untuk dua nombor.
2 nombor. Contohnya nombor uh, 15 dengan 30. So apa greatest common divisor dia? 15 dengan 30?
5.
Betul. Bukan 3.
Tak 5.
Sebab dia akan ambil yang terbesar.
Terbesar.
So apa gunanya kita belajar pasal GCD ni dalam kriptografi? Kenapa? So that's why benda tu saya tahu lah most korang mungkin tak boleh jawab, tapi itulah kenapa kita belajar GCD, kita belajar pasal kongruen. Okay, kongruen pula apa? Apa fungsi kongruen? Kongruen? Siapa ingat lagi kongruen? Jadi 3 dash. A congruent to B mod N. Apa maksud benda? A congruent dengan B mod modulo dengan N. Itu maksudnya? Tak ingat dah.
Have the same remainder.
Have the same remainder. A dengan B ada same remainder. So kalau kita perasan modulo ni dengan GCD ni is a process of factorization. Kita nak factorization so that kita nak dapatkan the very basic is a prime number lah. Itu the key of the main component of asymmetric algorithm lah, such as RSA. Sebab apa? Dia nak tentukan nombor prime number tu adalah betul adalah prime number lah, dan juga nombor tu adalah betul prime number dan dia bukan nombor yang kecil. Dia adalah nombor yang sangat besar. So macam saya pernah cakap kan, kalau nombor terlalu besar, kadang-kadang kita boleh anggap dia prime number. Sebenarnya the correct term is it is a probable prime. Probable prime ni maksudnya kita hanya boleh agak je benda ni adalah probably prime. So dia ada proses lah. Dia punya calculation lah. So masuk kita kepada chapter 4 ni. Okay, saya rasa dia refresh balik penggunaan GCD dalam Euler-5 function ataupun dipanggil Euler-Totian function lah. Saya rasa saya nak tunjuk video. Most of this lecture hari ni saya akan tunjuk video. Sebab apa? Kalau saya explain nanti takut lagi pening, saya pun pening. Tapi kita akan start dengan apakah itu RSA dulu lah. Boleh ya?
Boleh, Doktor.
Boleh, Doktor.
Okay, sekejap saya share. Okay, boleh nampak?
Boleh nampak.
Boleh, Doktor.
Alright. Boleh dengar?
Dengar, Doktor.
RSA stands for Rivest, Shamir, and Edelman. That's actually the last name of the three gentlemen that created the algorithm back in 1977. RSA is by far the most popular asymmetric encryption algorithm in use today. What it does is it creates a pair of commutative keys. What that means is you get a set of keys where you can encrypt with one of the keys and decrypt with the other, and it doesn't matter which order you go in. Everything we had discussed in a prior lesson of this module with Pam and Jim and what they can do with their private and public keys is an example of what RSA can do. Now, the reason I bring this up is because there are other asymmetric encryption algorithms, for instance, Diffie-Hellman and the digital signature algorithm. Those work slightly different. Those don't create a commutative set of keys. That's only RSA. Now, we'll unpack Diffie-Hellman and digital signature algorithm later on in this course. In this lesson, we're going to be focusing on the RSA algorithm. This slide and the last slide of this particular lesson is all you really need to know about RSA. What we are about to do next is to go into the math of the RSA algorithm. The purpose of this is to prove the commutative property of asymmetric encryption. At no time will you ever have to manually redo the math to make sure a particular server did it correctly. The only purpose of showing you the math is to prove this behavior. If you're anything like me, you were probably told at one point that asymmetric encryption allows you to encrypt the public key and decrypt the private key and so on. But it didn't actually click for me until I saw the math. So that's why I want to bring you through the math as well. If math is not something you're interested in, by all means, go ahead and skip forward to the last slide in this lecture where we discuss the security of RSA. For the rest of us, we are going to look at the RSA algorithm. Now, before we look at an example of the RSA math, we have to review a few math terms. There's 4 words we have to define before we can look at RSA. Starting with the word factor. A factor is simply any numbers you multiply to get the original number. For example, these are the factors of 12. I can multiply 1 and 12 to get 12, or 2 and 6 to get 12, or 3 and 4 to get 12. Hence, any one of these is a factor of 12. Keep in mind, the numbers don't have to be said in their pair. For example, I can say 2 and 3 are factors of 12. I don't necessarily have to pair 3 and 4 together or 2 and 6 together. Any numbers you can multiply the original number is a factor. Here is another example. Here are the factors of 7. You'll notice 7 only has 2 factors, 1 and itself. Every number will always be divisible by 1 and itself. But when a number is only divisible by 1 and itself, you get what's known as a prime number. 7 is a prime number. You'll notice that 7 only has 2 factors, 1 and itself. That's what makes it prime. Here are examples of other prime numbers. Any of these numbers only have 2 factors, 1 and themselves. Another way of defining a prime number is simply any number that's only divisible by 1 in itself. These 2 definitions are pretty much the same. The next math term we want to discuss is what's known as a semi-prime number. A semi-prime number is a number whose factors are prime. For example, 21 is a semi-prime number, and the factors of 21 are 1, 3, 7, and 21. Now, every number is always divisible by 1 and itself, so we can ignore those. The only remaining factors of 21 are 3 and 7, and you'll notice those are both prime numbers. That's what makes 21 a semi-prime number. Here's a hint. Anytime you multiply 2 prime numbers, the result is always semi-prime. So I can multiply 3 and 7 to get 21, and 21 is semi-prime. I could have also multiplied them to get 55, and 55 is a semi-prime number. So anytime you multiply 2 prime numbers, you get a semi-prime number. Finally, the last term we have to review is modulo, and that sounds more complicated than it is. All modulo is simply remainder division. For example, if I gave you the problem 13 mod 5, what I'm asking you is to tell me what's left over after you divide 13 by 5. Well, 5 can go into 13 twice evenly. That'll get you up to 10, and you have 3 left over between 10 and 13. Another example, if I were to give you 21 mod 5, I'm asking you what's left over if you divide 21 by 5. Well, 5 can go into 21 4 times evenly. That'll get you to 20, and you have 1 left over. And a final example, if I 25 mod 5, I'm asking you what's left over if I divide 25 by 5. Well, since 5 can go into 25 evenly, there's 0 left over. If you understand these 4 terms, you are now ready to actually see the math behind the RSA algorithm. There are 2 steps to the RSA algorithm. The first step is generating keys. The second step is actually using them for encryption and decryption. So here we're going to focus on the first step, generating keys. The first thing you have to do is select 2 prime numbers. We're going to call these numbers P and Q, and for the sake of this example, our prime numbers are going to be 7 and 19. The next thing you have to do is then multiply them together. you're going to multiply P times Q. So we'll do this together. That gives us 7 times 19, which gives us 133. We're going to call this value n. Now, given what we just discussed, can you identify what type of number 133 is? Hopefully you're able to put together that 133 is a semi-prime number, because the result of 133 came from multiplying two prime numbers. Next, we're going to calculate the totient. Now, the definition of the totient is actually pretty deep in the mathematics world. You have to understand things like Euclid's algorithm and the phi of n and a bunch of different things. I don't know math to that degree, but I do know that apparently to get the totient of a semi, all you have to do is subtract 1 from each of the primes and multiply them together. And this I can do pretty easily. So for us, our two prime numbers were 7 and 19, which means I'd be multiplying 7 minus 1, which is 6, times 19 minus 1, which is 18, and that'll get me 108. We're going to call this value t. Now that I have my prime numbers, my n number, the product, and my totient, I can now calculate a public key. The public key must match 3 conditions. The first, the public key has to be a prime number. The second is that it has to be less than the totient, that's 108. And finally, it cannot be a factor of the totient. So let's run through the example 3. Well, 3 is a prime number, so it satisfies the first requirement. 3 is less than 108, so it satisfies the second requirement. But let's see if 3 is a factor of the totient. Well, one way of calculating factors is by taking the number and finding the modulus when divided by 3. If you get a 0, this tells you 3 is indeed a factor of the totient, which means we cannot use 3 as a public key value. There are many values that we could use, however. For example, 5. 5 is prime. 5 is less than the totient, and if we did the exact same math, 108 mod 5, you'll see the remainder, meaning 5 is not a factor of the totient. So 5 would totally be acceptable for this example. Now for the sake of my slides, we're going to go ahead and use the public key value of 29. 29 is a prime number. 29 is less than 108, and 29 is not a factor of 108 because there's a remainder when you do the modulus operation. So our public key value, which we're going to call E, is going to be 29. And now that we have a public key, we can do the last step, which is to select a private key. Now the private key must only match one condition, but it's a slightly more involved condition. Key must meet this condition. If you multiply the private key and the public key, and then divide it by t, our totient, the remainder must be 1. Another way of looking at it is it must make this statement true. Now, for the sake of these slides, we're going to use the private key value of 41, but let's go ahead and punch it through this formula to see if it meets that condition. I'm going to take my private key, which is 41, and I'm going to multiply it by my public key, which is 29, and then I'm going to figure out the remainder when divided by the totient, which is 108. If I hit enter, you'll notice the result is 1, which means the private key value of 41 does indeed match this condition. So now that we have public and private keys, let's actually use them for encryption and decryption. For encryption with RSA, what I'm going to do is take the message that I want to encrypt and raise it to our public key value. Then I'm going to figure out the remainder when divided by n. That's going to get me the ciphertext. To decrypt, I'm going to take that ciphertext and raise it to the private key value, and then figure out the remainder when divided by n. And if RSA works the way it said it does, that should get me the same message that I started with. So let's go ahead and test it. We're going to use a message value of 60. 60 is going to be our starting message. And we're going to through these formulas to prove how RSA works. So let's start by encrypting with a public key and then seeing if we can decrypt with a correlating private key. So to encrypt with the public key, I'm going to take my message, which is 60, and I'm going to raise it to 29, which is my public key. 60 raised to the 29th, that gets me that, and I'm going to figure out the remainder when divided by 133. The result is 86, which means 86 is the ciphertext of encrypting this message, 60, with this public key. Theoretically, I'll be able to use this formula and my private key to decrypt that to the original message. So let's give it a shot. If I do 86, which is my ciphertext, and I raise it to the 41st power, then I figure out the remainder when divided by 133. I hit enter, you'll see that I was indeed able to land back on 60. So this proves that RSA works the way it said it does. I was able to encrypt the message of 60 with the public key and decrypt the resulting ciphertext with the private key. But remember I told you that RSA is commutative, which is to say you can encrypt with the public key and decrypt with the private key, or you can encrypt with the private key and decrypt with the public key. So we're not quite done proving how RSA works. Let's go ahead and public key and the private key in our formulas and see if we can still encrypt and decrypt and result with the same message. So let's encrypt the same message, except this time we're going to do the encryption with the private key and the decryption with the public key. So what I'm going to calculate for encryption with the private key is 60, our message, raised to our private key value, which is 41. And then I'm going to figure out the remainder when divided by 133. And that gets me 72. This is now the ciphertext after encrypting with the private key. So let's see if I can take that ciphertext and decrypt it with the public key. So again, I'm going to take 72, my ciphertext, and I'm going to raise it to the public key of 29. Then I'm going to figure out the remainder when divided by 133, and you'll see that that lands me back at the original 60. So now we have just proven RSA. We've shown you how to generate keys, and we've showed you how to encrypt with the public key, decrypt with the private, and that you can also encrypt with the private key and decrypt with the public. That is the math behind RSA. Now, of course, you and I use very small numbers for this example. In reality, RSA uses much bigger numbers. But how secure is RSA? Well,
Okey, saya tunjuk video sampai situ je. Okey, boleh faham?
security of
boleh,
RSA lies.
Boleh. So, at the end of the calculation tu, dia beritahu yang apa ni, kalau RSA dia encrypt pakai public, decrypt pakai private. So, tapi dalam apa ni, kiraan apa ni, RSA punya algorithm tu, kita juga boleh terbalikkan key. Tapi proses dia yang sebenar, yang sepatutnya kalau dalam RSA, kalau contohnya dia pakai dalam apa ni, online banking ke sebagai contoh lah, dia akan encrypt pakai public lah dan decrypt pakai private. So masa bila sebenarnya dia akan encrypt pakai public, encrypt pakai private, decrypt pakai public?
Lepas dia buat three-way handshake tu lah, dah buat transport layer tu, yang white tu, online banking kan. So
Okay.
dah exchange dia punya key masing-masing. So bila nak hantar data, nak request server tu, baru dia akan decrypt data dekat client tu. Pakai public key tu, yang server kasih.
Saya tak faham sekejap. So masa mula dia pakai encrypt pakai apa?
Mula-mula dia pakai TLS dulu untuk encrypt communication.
Tak, soalan saya, dia masa bila public dan private key tu digunakan, okay, the first encryption, dia encrypt pakai apa? Public ke private?
The first dia pakai private lah.
Private.
First dia pakai private, then
Private.
dia pakai public.
Betul.
So bila dia spesifik teknik dia panggil Diffie-Hellman key exchange. In fact, Diffie-Hellman key exchange ni datang sejarah dia asal-asal dia sebelum lagi RSA ada. Sebelum digunakan dalam RSA lah. So Diffie-Hellman key exchange ni maksudnya contohnya dia tak kenal sebelum ni antara diorang kan, dalam satu group of people ni dia tak kenal. So that's why dia akan buat apa ni, a session lah, dia panggil Diffie-Hellman ni, dia panggil digunakan untuk session key. Siapa pernah dengar Diffie-Hellman?
Dengan nama je lah Diffie-Hellman.
So dia banyak digunakan dalam network punya ni lah, network communication. So maksudnya kalau RSA dia digunakan dalam digital signature lah, digital signature punya teknik. Tapi dalam RSA dia kena ada orang kata apa, third party tu untuk generate dengan distribute the key. So dia panggil certificate authority ataupun ada macam-macam term lah dipanggil, tapi basically a third party lah, satu parti yang tak ada kena-mengena dalam group of communication tu. Kalau online banking, kita adalah client, kita ada group kita masing-masing, dia CA ataupun dia yang manage the key generation and distribution is daripada pihak Maybank lah. Contohnya lah kalau Maybank 7 ke CIMB Click ke. So sebelum dia adakan RSA untuk application of PKI ni, dah ada dah dalam network, dia panggil development key exchange. So sebelum kita nak communicate dengan orang tu, kita nak bagi kita punya key. So macam mana kita nak bagi kita punya key? Kita akan encryptkan kita punya key tu, kita punya public key dengan kita punya kita akan encryptkan public key kita tu dengan kita punya private key. Faham? Private key kita seorang saja tahu public key maksudnya semua orang tahu. So that's why saya A, saya nak communicate dengan B, dia kena tahulah saya punya public key. So sebelum ada PKI, the key distribution tu tak ada. Maksudnya CA tak ada third party. So maksudnya saya kena bagi saya punya public key kepada B. Macam mana saya nak buat tu? Saya encrypt dengan private key saya. Saya bagi this is another situation lah. Tapi saya encrypt dengan private key saya. Dia pun boleh decrypt dengan public key saya juga. Dia ada satu situation ni, development key exchange. Siapa familiar dengan development key exchange? Untuk session key dalam network. Tadi Zul kata pasal TLS tu macam mana? TLS tu berfungsi.
Dia orang buat three-way handshake dulu. Tapi tak silap saya lah, at the same time dia orang exchange key.
Okay. Saya baru ingat. The session key tu dia separate pair of key lah. Dia bukannya key yang sama. So basically, misalnya semua group tu dia dah ada dia punya, everyone dah tahu dah public dan private public key masing-masing, dan orang lain tahu kita punya public key. Tapi kita nak ada secret punya communication within the group. So that's why dia panggil session key lah. So that's why kita akan encrypt kita punya public key dengan kita punya private key. Kita akan bagi kepada B, macam contoh saya A dengan B tu akan decrypt dengan dia punya dengan public key saya, public key untuk the general punya public key, so that dia boleh dapat secret punya public key saya lah yang saya encrypt tadi. Boleh faham ke tak? Faham. The implementation of basically development, dia akan encrypt dengan public key, decrypt dengan private key. Kalau terbalik. Development dia akan encrypt pakai private key, decrypt dengan public key. Kalau RSA dia akan encrypt pakai public key, dia akan decrypt pakai private key. Dia terbaliknya itulah. My point is the session key tu dia berbeza kalau penggunaan dengan RSync, sebab whereas RSync tu dia ada dia punya PKI yang akan generate dia ada certificate authority yang untuk generate dan distribute the key. Okey, berbalik kita pada slide, sebab saya masukkan RSync ni so that korang boleh kaitkan dengan matematik punya basic notion of the ni lah, pengiraannya. Okey. So dalam perkiraan how to calculate tadi, kita nampak tadi dia kata pasal totian kan. Totian tu adalah phi lah sebenarnya. Phi. Dia sama lah. So apakah itu totian atau Euler phi function ni? Ialah GCD A dengan N where the it is equal to 1. So ingat lagi GCD kan? Ingat lagi?
Great common divisor.
Tadi cik saya pernah beritahu. Saya takut ada yang dah lost ni. Tapi itulah, saya ada satu video lagi yang akan kita akan tengok on the totian ataupun phi function ni dan juga Fermat little theorem lah. Itu yang yang berkait dengan dia RSA punya calculation. Okay, and then kita juga akan tengok on probability testing, Miller-Rabin test. Saya tak nak tunjuk ni secara detail Miller-Rabin test ni. Basically dalam RSA ni dia ada bahagian cryptanalysis ni, how to determine the factorization of that prime number. So that's why ada Miller-Rabin test ni. It's a cryptanalysis punya ni lah. Kalau siapa yang boleh breakkan factorize that prime number yang digunakan dalam RSA tu, maksudnya tak secure lagi lah. So that's why cryptanalysis is the process of breaking the crypto algorithm. So Miller-Rabin test ni is one of it lah. Okay, saya akan tunjuk video on. Hello, boleh dengar kan?
Boleh sir.
Boleh doktor.
Dia macam terputus sekejap ni. Sekejap Okey, jap. Okey, boleh nampak screen saya?
Boleh
Boleh
doktor.
sir.
So we are going to go over some of the basic properties of Euler's totient function, which is a very important function in number theory that pops up in a ton of important theorems. Now, Euler's totient function is usually denoted by the Greek letter phi. So we say 5n is Euler's totient function, and we define that totient to be the number of integers on the interval 1 to n inclusive that are relatively prime to n. Now, relatively prime is another word for coprime, meaning that the number shares no prime factors with n. So let's look at one example. What is the totient function of 6? Well, we know that we're looking at the interval from 1 to n. In this case, n is equal to 6. So all of the integers between 1 and 6. That's going to be 1, 2, 3, 4, 5, and 6. So we want to find the number of integers in this set that have no common factors with 6. We know that 6 is equal to 2 times 3. This is the prime factorization. And therefore, we need to find the numbers that don't have 4 or 3 in their prime factorization. That's going to be 1, not 2, because that includes a 2, not 3. 4 includes a 2 as well. So even though 4 doesn't divide 6, it still has a common factor, so they're not coprime. On the other hand, 5 definitely is, and then of course 6 is not. So we see that there are 2 integers on 1 to 6 that are coprime to 6. They share no factors. And therefore 5, 6 is equal to 2. Now we're going to look at some specific examples of the totient function when we look at some prime numbers. Let's start with the simplest case of the Euler's totient function. What is the totient function of a prime number? So in this case, we're saying that p is prime. Well, remember that the prime factorization of a prime number is just p. It is its own only prime factor. And as a result of that, if we look at the interval 1, 2, 3, and so on, up to p, none of these numbers in here are going to share any factors in common with p, because in order to share a factor with p, they would have to include p in their prime factorization. But it's impossible to include p in your prime factorization and still be less than p. You'd have to be at least equal to p, which means that all of the here are coprime to p. Of course, p is not coprime to p because it's equal to itself. Now we want to find the number of integers that are coprime to p. That's going to be the number of integers in here. Well, that's all the numbers on the interval 1 to p except for p. And the number of numbers in that interval is just p minus 1, since we're not including p. So for any prime number, the totient function of that prime number is equal to p minus 1. For example, the totient function of 13 is equal to 12, since 13 is a prime number. So now we've seen the simple example of a prime number. Now we're going to look at a slightly more general result, which is the totient function of p to the power of some number. So p is still a prime number, but now we're choosing some positive integer as an exponent. In order to figure out what this is, we first need to look at the prime factorization. Now, of course, because p is prime, the prime factorization of p to the a is going to look like p times p times p times and so on. So the only prime factor is p. What that means is that all of the numbers that share a factor with p to the a are just all the multiples of p. What are those? Well, that's going to be 2 times p, 3 times p, 4 times p, and so on, all the way up to p to the a. This is the last number in our interval. And we can also write p to the a as p to the a minus 1 times p. The reason that we do this is because our goal here is to count the number of integers in this set. And we can see that all of these are just multiples of p. So the number of multiples there are is 1, 2, 3, 4, 5, 6, up to p to the a minus 1. That's how many multiples of p we have. So we're looking at p to the a minus 1 numbers that share with p to the a. But remember that our goal is not to find all the numbers that share a factor with p to the a. Our goal is to find all the numbers that are relatively prime. In other words, they share no factors with p to the a. And that's going to be all of the numbers except for these ones. So the way that we can do that is by thinking first, how many numbers are in the interval? That's going to be p to the a, because we're looking at the interval from 1 to p to the a. Now we want to subtract all of the numbers that share a factor with p to the a. Well, that's just going to be all the numbers in this list, and we know there are p to the a minus those. So phi of p to the a is equal to p to the a minus all the numbers in this list, which are p to the a minus 1. This is the number of multiples of p. And we can factor out a p to the a minus 1 here to get p to the a minus 1 times p minus 1. So that is the Euler totient function. It counts the number of integers on the interval 1 to n that are co-prime to n, that share no factors with n. For a prime number, we saw that the totient function of p was equal to p minus 1, since all the numbers other than p share no factors with p. And then we also saw the totient function of p to the power of some number a was equal to p to the a minus 1 times p minus 1.
Okey, dia faham.
Agak pening sikit nak brain.
So dia nak explain where does the calculation of totient atau phi itulah dalam calculation dalam apa ni, dalam RAC punya calculation tadi. Kan kita perasan kan, kita kena calculate, cari P dengan Q, and then N equal to PQ, P darab Q, and then kita kena cari totient atau phi, which is P minus 1, and then Q darab dengan Q minus 1, and so on lah, dia punya step dia. So basically that's the reason of calculating the total atau ni lah. Okay. Moving towards our notes. Okay. Saya ada juga video on Fermat little theorem ni. Nak tengok ke tak? Ke boleh tengok sendiri?
Boleh je kalau doktor nak tunjuk.
Okay, so dia punya presenter pun orang sama jugalah. Boleh nampak saya punya skrin?
Boleh doktor.
New Vaseline Gluta-Hya Pro Age with
Talk about Euler's-Tauschent theorem and Fermat's little theorem. Now, Euler's-Tauschent theorem is the statement that if A is co-prime to n, in other words, if the greatest common divisor of A and n is 1, then A to the power of phi of n is congruent to 1 mod n. In this case, phi of n is Euler's totient function, so a number of integers from 1 to n that are co-prime to n. As an example of this theorem, if we choose n equals 100, then you can prove that 77 to the power of 40 is congruent to 1 mod 100. So this statement right here is an example of applying Euler's theorem. Now, in the proof of Euler's-Tauschent theorem, I'm going to use a few properties that have to do with co-prime numbers and how they interact with modular arithmetic. So if you aren't familiar with any of the identities that I use, you can check the link in the description where I go through the derivations. The start.
Okay, saya akan skip terus. Ni pasal dia still mention pasal Tauschent theorem. Saya akan skip sampai ke Fermat lah.
Of the proof of Euler's-Tauschent theorem is pretty simple. We're going to construct x sub I is congruent to a times 0. To have axi congruent, these are all of the numbers, every single number between 1 and n that's incongruent and co-prime to n. They both contain words. We can say that every number in T prime is congruent to one element in T. Every single element in T on the right, those two products will be congruent to mod n. So what we're going to do is multiply all of the numbers on the left with overall congruent I. So the phi of n is phi of n copies of that through any time.
Aduh, tak ada mention pula spesifik Fermat ni. Okay, tak apalah, saya skip lah. Apa ni, this video ni.
Time A is.
Saya akan pergi kepada Miller-Rabin test untuk cari factorization punya ni lah, catalysis lah. Boleh
Boleh doktor.
Doktor, kalau nak tanya untuk RSA nak dapatkan nombor awal tadi kan?
Nombor apa?
Kan tadi kan dia nak encrypt nombor 60 kan? Ciphertext dia 86 kan satu slide dia kan?
Okay.
Itu kalau dia bagi number. Tapi kalau dia bagi string, boleh ke kalau kita pakai table yang dekat symmetric punya slide tu? Yang 0 sampai 25 tu?
Bukan. Jangan confuse dengan simetrik. Simetrik lain, asimetrik lain. Tapi simetrik pun sama. Contohnya lah. Itu kalau dia bagi contoh string. Kalau benda tu daripada voice macam mana?
Daripada voice?
Daripada voice.
Oh yelah betul lah kan.
Kalau audio encryption nak macam mana? Video encryption? Video okey lagi kalau benda yang analog. Macam mana kita nak encrypt benda yang analog?
So kena tukar jadi binary tukar jadi nombor.
Ya, betul.
Oh, number lah.
So, sama ada dia akan tukar kepada 60 tu, dia is just an integer. Tapi kalau dalam encryption, kita akan tukar juga kepada binary, and then certain system dia akan pakai hexadecimal. So not to be confused lah. Memanglah matematik ni memang dalam integer kan. Tapi everything will be converted lah. The format is bukan, jangan confuse dengan simetri lah. Simetri itu pun sama juga, dia akan convertkan juga. Okay, boleh faham?
Lepas tu doktor, kalau binary tukar jadi hexa kan, tapi dia ada huruf. Ada A, F ke benda-benda kan. Yang tu macam mana nak kira pula kalau ada huruf?
Okay, daripada binary, kalau kita nak guna untuk matematik, kita tukar kepada apa? Integer ni based on apa? Apakah format dalam komputer untuk integer? Decimal lah, decimal.
Decimal.
Integer tu adalah decimal. Okay boleh faham?
Okay, faham. Bukan nombor, okay, faham.
So dia ada binary, ada decimal, ada hexadecimal. Apa lagi? Okay, alright. Saya nak tunjuk. Kita dah macam dah sejam dah ni. Takut nanti korang lagi pening. Saya takut ada yang ketinggalan. Can you share the link dekat group WhatsApp? Nanti saya akan share the link all the video lah semua. Okay, sekejap Gila rabbit test.
I'll be explaining how to find if a number is prime using the Miller-Rabin primality test. So what is a primality test? Well, basically, it's a function that takes in a positive integer n, and it tells us whether that integer is prime or composite. And this has many applications in, for example, cryptography, where we have to find very large prime numbers. So before we get into the explanation, it could be helpful to understand a little bit of modular arithmetic and a little bit of algebra, but I'll explain the necessary symbols and notation here. So first thing to know about modular arithmetic is that it's basically about the study of remainders when you divide one integer by another. So the only important notation that we need to understand is this. A is equivalent to B mod. So for the purposes of this video, this basically means that when we divide A by n, we get a remainder of B. So for example, if we divide 52 by 10, we get a remainder of 2. And we would write that as 52 is equivalent to 2 mod 10, because when we divide 52 by 10, we get 5 and then a remainder of 2. So that's basically what this notation means. Also, if we write A is equivalent to 0 mod n, that basically means when we divide A by n, we get a whole number. We get an integer. So that means that A is divisible by n, or n is a divisor of A. So that's all the necessary notation for modular arithmetic. Okay, the next that we need to understand before we go into the explanation is called difference of squares. And this is basically really simple. It tells us that x squared minus y squared equals x minus y times x plus y. And you just get this if you expand it out. This is just a very common factorization. Just remember that x squared minus y squared is equal to x minus y times x plus y. Okay, so now we can actually get into the test itself. So we're given an integer n, and we need to do a function. And we need to tell if n is prime or composite. For now, we'll assume that n is greater than 2. So in order to tell if n is prime or composite, we're going to assume it's prime. And then if ever we arrive at a wrong conclusion, if we ever arrive at a false statement, that means that our original assumption was wrong, that n was prime, and that means that n is composite. So if we ever get something wrong, then we know that n is composite. So now, what we're going to do is we're going to pick a random integer a between 1 and n minus 1. Random integer a between 1 and this can be any random number. So our next step comes from the mathematician Fermat. Right? His little theorem tells us that a to the n minus 1 is equivalent to 1 mod n, if n is prime. And remember that what this means is that when we take a to the n minus 1 and we divide it by n, we get a remainder of 1. So what we can do next is we can write a to the n minus 1 is equivalent to 0 mod n. Because in modular arithmetic, when we have this equivalent sign, it's basically equivalent to the equal sign in regular math. So we can subtract and add numbers on both sides. So we get a to the minus 1 minus 1 is equivalent to 0 mod n. Now remember the difference of squares factorization? Yeah, n is prime, then n minus 1 must be even. So we can do a difference of squares factorization. We can do a to the n minus 1 over 2 minus 1 times a to the n minus 1 over 2 plus 1 is equivalent to 0 mod n, because this expression over here became this expression over here using our difference of squares factorization. So now that we have this, we can take a look at the left term. If n minus 1 over 2 is even, then we can factorize this even further. We can make this become a to the n minus 1 over 4 minus 1 times a to the n minus 1 over 4 plus 1 times a to the n minus 1 over 2 plus
Doctor
1
gelap screen
is
apa
equivalent
gelap
to 0 mod n. And notice that one term over here, this term over here became two terms because, again, using difference of squares. And this implies the n minus 1 over 2 has to be even. That doesn't have to be the case. If n minus 1 over 2 is already odd, then we just stop at this step. But if it's even, then we can continue to factorize it. So if it's even, we can factorize it like this with a to the n minus 1 over 4. If this exponent is still even, if n minus 1 over 4 is still even, then we can factorize it even further, still using difference of squares. And that would become a to the n minus 1 over 8 minus 1 times a to the n minus 1 over 8 plus 1 times a to the n minus 1 over 4 plus 1 times a to the n minus 1 over 2 plus 1. And this is all equivalent to 0 mod n. So we can keep doing this. We can keep factorizing the leftmost term, the minus 1 term, using difference of squares if the exponent is still even. So we do this until the exponent becomes, so for example, we end up at a to the n minus 1 over some power of 2 minus 1 times a to the n minus 1 over 2 some power of 2 plus 1 dot 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 times a to the n minus 1 over 2 plus 1, and this is equivalent to 0 mod n. And then once we get this big expansion, we know that we can't expand this left term any further, because if we could, then we should do it even further. So this exponent has to be odd. And what we do now is that if n is prime, that's what we assumed at the beginning, and we're looking for a contradiction, then n has to divide one of these terms. Because this left-hand side being equivalent to 0 mod n, remember, that means this left-hand side is divisible by n. So n has to divide into one of these terms. And you might think that obvious, but it's not. If n is not prime, then it doesn't have to divide into one of these terms. So for example, we consider the number 4. 4 is not prime, and it divides into 12. But 12 is equal to 2 times 6, and 4 doesn't divide into any of these. 4 doesn't divide 2, nor does it divide 6, but it does divide 12. And this is just saying that if n is prime, it does have to divide at least one of these terms on the left-hand side. So we check these one by one through the powers of 2, and then if at least one of them is divisible by n, then we know our condition is satisfied and nothing was violated. However, if none of these are divisible by n, then we know that n, because at the beginning we assumed that n was prime and we worked our way to a conclusion. And if this conclusion is false, if n doesn't divide any of these terms, then we know n is composite, because it violated our original assumption that n was prime. So to summarize, we were given a value of n, we took a random value of a between 1 and n minus 1, we followed these steps, we used the difference of squares factorization, and then we arrived at a conclusion. If n divides at least one of these, then n is probably prime. However, if n divides none of these, then n has to be composite. If n passes this test, there's a 3/4 probability that we are right. So if it passes this test, there's a 3/4 probability that n is actually prime. However, if it passes, there's actually a 1/4 probability n is composite. So this test isn't perfect. It's only 75% right? Well, no. Remember, at the beginning, we chose a random value of a. So if we choose a different value of a, then our chance of being wrong goes from 1/4 to 1/16. And you can see where this is going. If we use, for example, 40 values of a, if we use 40 values of a, then our chance of being wrong goes to 1/4 to the power of 40. And this is a very small chance of being wrong. This is equal to 2 to the negative 80. And for scale, we can say that if we did one of these tests every second since the start of the universe, which is 13 million years ago, then we would still only have a 1 in 1 million chance of being wrong. So this test is very accurate as long as we do many different values of a, and it doesn't have to be even a very large value of a. It can even be 40. So if we do this test many times for many values of a, and n passes all of these tests, then we are probably right in that n is prime. So that's the basics of the Miller-Rabin primality test. if we're given an integer n, we can tell if it's prime or composite. But still, this is a probabilistic test. Even if it's very, very good, there is still a very, very, very small chance of it being wrong. So we can't be certain if it's prime or not, but we can be very, very sure. So that's the Miller-Rabin primality test explained. I hope this helped you out. I hope you learned something. If you have any feedback, the comments below. And thanks for watching. Goodbye.
Okay. Boleh faham? So
Betul.
dalam video tu pun tunjuk pasal apa ni format kita theorem lah. Dia continuous lah. Maksudnya kita kena faham daripada phi of n, Totian tadi. Lepas tu kepada format kita theorem and then baru ke Miller-Rabin test lah. Ya, nak tanya Ari.
Soalan-soalan ni masuk exam kan, calculation ni. Kalau nak buat latihan buat kat mana doktor? Doktor recommend?
Tak, itulah saya takkan masukkan soalan matematik ni dalam test. Jadi hanya basic lah. What is Miller-Rabin test ke, macam mana, what is the formula for Miller-Rabin test ke. Like that lah. Saya tak ada matematik proving of the equation. Sebab to be honest lah, yelah, all of that calculation tu dah digunakan pun dalam komputer. Tapi kenapa pentingnya Miller-Rabin test ni? Kenapa? Saya mention tadi di pasal cryptanalysis, kan? Kita nak breakkan RSA tu. So kenapa kita kena tahu Miller-Rabin test ni? The logic is, kenapa? Miller-Rabin test ni dia punya result tadi dalam apa? Tanya soalan logik je ni. Saya tak nak ke deep on the maths lah. Semua tak tahu. Kalau tak tahu saya kena buat quiz ni. So that korang kena ni.
Rapid test saya Google, dia kata untuk buat initial investigation lah, nak check sama ada vulnerability dalam cryptographic tu, algorithm tu.
Dia vulnerability is not the correct term lah. Tapi yelah, cryptanalysis is for breaking the algorithm. Kita nak apa ni, nak tahu apa ni, sama ada betul ke tak apa ni the algorithm, contohnya RSA, dia betul tak pakai prime number. Tapi yelah, in digital world, dalam komputer, kita assume komputer boleh lah apa ni calculate betul-betul prime number yang very besar. Tapi this is a very large prime number tau. So that's why Miller-Rabin ni is just a probability punya test. So that's why dia punya result tadi dalam apa ni, dalam probability dalam peratusan, apa ni, quarter, 75% it is a prime number. So that's why Miller-Rabin test is still penting lah dibuat. Sebab dalam apa ni, dalam digital world sekalipun, dia nak generate a prime number, a very big prime number pun tak semestinya benda tu adalah prime number. So sebab apa, that's why Miller-Rabin ni pun dah ada dah. That's why kita pun kena run apa ni, ada developer yang good. Contohnya dia nak gunakan RSA dalam dia punya application. So dia akan juga codekan apa ni, Miller-Rabin test ni. Contohnya, ada contoh sebenarnya, ada banyak dalam apa ni, dalam Python dan certain language yang dah di develop untuk buat Miller-Rabin test ni, untuk check sama ada dia punya prime number tu, dia punya high probability, dia it's just a probability lah, percentage lah, betul adalah prime number. Sebab kita nak guna prime number it's very big lah, it's a very big punya prime number. So that's why dia punya probability dia sepatutnya very less chances yang benda tu bukan prime number lah, ataupun high chances, high percentage, sepatutnya more than 75% it is a prime number lah. So only on the probabilistic. Okay, boleh faham? Explanation saya ni mungkin keluar dalam ni. dalam test. Okey ke?
InsyaAllah, sir.
Okay. So this is the ni kita balik kepada notes kita. So ada prime factorization. Okay, pemat. So basically yang dah explain tadi lah. The way yang kita nak tahu dia adalah apa ni prime number adalah kita kena buat factorization. Kalau number tu terlalu besar, macam mana kita nak buat factorization secara manual kan? So that's why ada apa ni Miller-Rabin test tadi. Okay, habis. Tapi sebenarnya ada satu lagi on apa ni video on logarithm. Dia sepatutnya memang ada dalam your punya syllabus lah. Di subjek punya syllabus. Okey, apakah itu log? Kat sini mention congruence modulo. Congruence, that's why saya mention pada awal kelas tadi, apakah itu congruence modulo. Mesti korang tahulah. Kan, betul kan? Congruence. A, congruence will be mod n. Itu congruence modulo lah. And then logarithm. Apakah itu logarithm? Siapa tahu logarithm tu apa?
Inverse function of exponentiation.
Uish. Ambil daripada internet ke macam Google lah.
Betul.
Logarithm ni basically the process of log lah. Log to the base. So instead of kita pakai the power exponential, kita akan convertkan kepada log lah. Log base 10 ke. Okay, saya rasa saya nak stop sampai sini kot. Saya tak nak peninggal lagi on mathematics punya calculation ni. So basically is what are the process behind the asymmetric punya algorithm lah, such as RSA. Kenapa ada probability testing, kenapa ada Miller-Rabin test ni? It is a process of cryptanalysis. How sebab yalah, it's not simple. Memang ada orang boleh kata apa ni, dia boleh create apa ni calculation yang very complex untuk jadikan cryptography algorithm. So that's why satu, kita kena provekan based on cryptanalysis. So that's why kalau kita nak buat process of apa ni asymmetric R&D lah, R&D on asymmetric algorithm, kita nak come up with our own algorithm. Dia ada 3 basic component. Saya pernah terlibat dulu dalam projek National Cryptography Algorithm yang military nak pakai. So basically the first one is the cryptography algorithm itself lah. What are sama ada kita nak pakai apa ni, asimetrik ke, simetrik ke, kalau simetrik, stream cipher ke, block cipher ke, and then the key management punya build up, maksudnya the development of key management, and then the last one will be the cryptanalysis. 3 benda ni memang kena ada kalau kita nak kalau kita nak develop our own punya cryptography algorithm. So that's why itu kalau kita nak buat algorithm kita sendiri. So that's why kenapa ramai orang still pakai AES, kenapa pakai RSA? Sebab dua-dua ni dah is a standard lah. Kalau simetrik memang pakai AES. Kalau RSA memang kalau asimetrik memang pakai RSA. Pasal both of these dah proven dah pun. Tak adalah memanglah memang ada selalu pun ada research on kata AES sekarang dah boleh break. Tapi dia boleh break in what condition? It will be a big debate lah. It will be a debate. And then certain conditions saja. Tapi towards this current punya implementation of AES, contohnya AES 256, tak boleh lagi di break. Memang tak boleh lagi di break. Maksudnya logically tak boleh di break lah. Kalau dia kata dia boleh break tapi ambil masa 1 juta tahun, itu tak logik lah. Sebab 256 is a big it's a big key. It's a long key yang sangat panjang kan, 256. So kalau ada orang tu ada super komputer, dan orang tu memang tak pernah tukar key selama 1 juta tahun, memanglah boleh break. Sama juga dengan RSA, dengan asimetrik. Kalau kita kita dah run the Miller-Rabin test mengatakan 75%, contohnya for that particular RSA kita guna satu key tu yang prime number dia contohlah kan very large, and then kita test on Miller-Rabin test, kita dapat probability dia adalah prime contohnya terlalu rendah, contohnya 50%. Still, maksudnya kita kena find out lah, kena cari prime number yang very yang different, yang very panjang lagi, sampai tahap Miller-Rabin test at least 75%, 1/4 adalah probable prime. Okey, faham ke?
Tak apa, doktor.
Saya nak faham, saya nak beritahu the logic is tu je. Kenapa, apakah dia apa? The explanation behind the symmetric. Kalau symmetric, kenapa proses dia apa? Substitution dengan apa ni? Substitution dengan apa?
Transposition.
Okey, asymmetric pula the apa ni? The prime number. Basically is around the prime number je. Tapi ada contoh lain lah. Contohnya apa? Dalam apa ni? Prime number yang di-generate daripada elliptic curve. Elliptic curve pun ada dia punya pembuktian dia sendiri. Tapi kalau dalam RSA, asymmetric ni, dia punya cryptanalysis is the process of factorization lah. Okey, ada apa soalan?
Daripada saya tak ada, doktor.
Okay. So next week kita akan tengok very deep lah macam mana how to develop the RSA, ada Rabin crypto system, L-Gamal dengan elliptic curve. This is all dalam asymmetric lah, asymmetric. So next week saya akan assign assignment 2. It's not simple symmetric versus asymmetric implementation. Saya nak kenapa ada reason jugalah. Kenapa orang pakai asymmetric, kenapa orang pakai symmetric. Okay, itu saya akan explain next week lah. Okay, kalau tak ada apa soalan.
Doktor. Yang public holiday Ahad tu cuti ke tak cuti? Bahaya kan? Yang di Pawali.
Memang cuti pun. Kat sini kan dia tu cuti. Public holiday. Week 6.
So hari Isnin. Tak ada kelas lah. So hari Isnin dah cuti lah. Kalau UiTM.
Itu siapa yang ada kelas tu lah kat ni. Tapi basically cuti lah. Kalau ayah Ahad memang gaji Isnin. Tapi yalah, our kelas ayah Ahad. Ayah Ahad memang di Bali. So memang cuti lah. Dekat dalam kalender akademik memang dah tulis lah pun Ahad memang cuti. Okey.
Okey, doktor.
So kelas, sorry. Sila.
Apa dia? Ada apa nak tanya?
So kita orang cuti 2 minggu lah dengan ke doktor. Dengan midterm sekali. 2 kelas.
Okay, by next week juga, minggu depan saya akan saya arrange. Hello, boleh dengar?
Dengar.
Okay, so by next week saya akan arrange lah which topik yang every group akan dapat. Tapi yang saya dah assign yang group 5 tu lah, Zulfaqli and the gang. Dia akan cuba, dia pun macam saya cakap lah, discuss dengan dia ada team jugalah. Kalau ada cadangan apa-apa, tapi the coordinator ataupun person in charge will be the group 5 lah. Okay, kita boleh tamatkan kita punya kelas hari ini. Thank you, goodbye, Assalamualaikum.
Salam, terima kasih doktor.
Terima kasih, doktor.
Thank you, doktor.
Thank you doktor.
Doktor. Saya dah share PDF tu.
Okay.